Hey folks, it is time for acids, bases, and salts. This is one of my favorite units, and hope you like it too. So first of all, you should be slightly familiar with acids and bases because you've talked about them in other classes like the living environment and possibly in middle school also. So yeah, hopefully some of this is familiar to you. Please also get out the acid and base reference tables, which are, just don't want to tell you the wrong ones, table K, table L, and table M. They're all on page 6. So those are the acid-base reference tables we're going to need. So general properties of acids. What is an acid? Well, they're, if you were to taste them, food-safe acids, sour. So think lemonade, think citrus, tomato, vinegar. pH scale. We will definitely talk about pH, but if you remember, low pH value. Now, hopefully you remember that 7 is a special number. Where'd it go? 7 is a special number. 7 is neutral. Neutral. So how about we just say below 7? Below 7. And starting at 0. So they conduct electricity in the aqueous state. Do you remember what aqueous means? That means dissolves in water. So an acid isn't going to be able to conduct electricity and have those movements of ions, the mobile ions, unless you put it into water. Then we can conduct electricity. Corrosive, they break things down. In solution, when they are breaking down into those ions, it produces H plus in solution. So some common examples, anything on table K. So if you were to turn there, hydrochloric acid and all the rest. So all of those, we've got, oh, look at me, I got it right there. Citrus fruits, coffee, that kind of stuff. Bases are the chemical opposite of acids. If you were to taste them, they would taste bitter. If you were to feel them, they would feel slippery. If you remember when we were doing tie-dye and you were wringing out your wet shirt, that slippery feel is unique to bases. Bases have a high pH value. Let's just say higher than 7, not necessarily 7. 7 is neutral. These also conduct electricity in the aqueous state. So once again, if you put a base into water, it breaks apart into the ions that will conduct electricity because everything is all about mobility, movement of electrons. Bases are also going to be corrosive. They're also going to burn your skin. However, in solution, this is going to produce OH minus, which if you forgot, this is called hydroxide. That's OH minus. So anything on table L is a base. So we've got, again, notice all of these are aqueous. And now I will admit that ammonia does not have that hydroxide like the rest of them do. However, it is a base. Household cleaners, yeah, so those are bases, the opposite. And we will talk later about what happens when you have acid and you combine them with base. Maybe we should take a step back and talk about what an electrolyte is, since acids and bases both are electrolytes. They conduct electric current when in the aqueous state. So acids and bases, they're both going to conduct electricity. Some are better than others. And also ionic solutions, so salts in water will conduct. So that's why this is called acids, bases, and salts. Those are the things that will conduct electricity. Again, if they have mobile ions, that's the only way you're going to get electricity to flow through. So anytime you see something covalent, like sugar, that's not going to be an electrolyte. Alcohols, so that would be something like CH3OH, which again, we have covalent bonding. So that would not be an electrolyte. You need mobile ions, and ions have charges, okay? So there are many different ways to define an acid, and so this guy, Svante Arrhenius, 1859, I think. Who cares? Dead white guy. What was his definition of an acid? So the Regents loves Arrhenius. So you should definitely know his definitions of acids and bases. And all of these are right. This isn't like atomic history where, we learned some things that were not right and then, we got better understanding. Arrhenius is considered correct. There are just alternate, also correct definitions for acids and base. So according to Arrhenius, an acid is anything that will give off H plus in solution. So H plus in solution. So for example, if we have something like HCl, that's an H. When HCl breaks apart into solution, what's it going to produce? It's going to produce H plus, and it's going to produce Cl minus. So since it produced H plus, we call it an Arrhenius acid. Arrhenius bases are anything that give off hydroxide or OH minus. Go back. So NaOH, remember hydroxide is a polyatomic, so that's going to stay together. So when you give that off, you're going to have sodium ions, Na plus, and hydroxide. And since it produces OH minus in solution, we consider it a base under the Arrhenius theory. Okay, so the Regents loves Arrhenius theory. Again, that's not the only correct theory, but it is one correct theory. So we talked about acids, we talked about bases. I think we've kind of piecemeal talked what a salt is. Salt is not just NaCl. It is not just NaCl. It is any ionic compound, as long as you don't have H plus and you don't have OH minus. Salts have what we call a lattice structure. So you see how we've got this organized kind of pattern, and these blue circles, these are in the smaller ones. These are Na plus, and this is larger Cl minus. Notice how they combine, they bond, and you see that we have these little square planes, and when they all come together, it would be cubes. We've already talked about how ionic solids have high melting points. So, ionic substances have high melting points, so they're solids at room temperature. Sorry, you can't read that. It says good conductors of electricity in the liquid or aqueous phase. Remember, table salt or any other ionic compounds will not conduct, what is going on here? Will not conduct in the solid phase, but as soon as you make those ions mobile, how would you get them to be mobile? Well, you'd melt it, which would be really challenging because they have a super high melting point. But if you also put them in water, aqueous, then you're going to get that conductivity. This is why these are also what we call electrolytes. I miss my pen. All right, here is another theory of acids and bases, also correct. On the Regents, for whatever reason, they don't like to call it Bronsted-Lowry, which were two different scientists who came together to form this theory. I'm guessing they are both dead white guys. Not exactly sure, but I'm pretty good bet that's going to be true. On the Regents, they call this alternate acid-base theory. Alternate to what? Oh yeah, who was that other guy? Arrhenius. That's an E. So it's alternate theory to Arrhenius. Now, if you remember, Arrhenius said acids are anything that gives off H plus, bases are anything that give off OH minus. It's all about producing in solution. But Bronsted-Lowry said that the acid is anything that's going to donate H plus, hydrogen donors. Bases are going to be anything that accepts, hydrogen acceptor. I don't know why they don't call it receiver. They usually call it acceptors. I don't know. I just really like this little picture. Here, have a proton. Gee, thanks. And so come on, man. So this gave away the proton. So whatever this thing would be considered acid. Whatever except the proton would be considered base. Now notice this has nothing to do with pH, nothing to do with how it tastes. This is another definition of acid which says acids give the proton away, bases accept. So let's figure out who is the acid, who is the base. Now, first of all, you might notice this double-sided reaction arrow, which means we have a reaction going this way, which we call the forward reaction, but we also could have a reaction going this way, which is called the reverse. So let's talk about what is happening. This tricks students up a little bit, so I want to clarify. So in the forward reaction, we're reading left to right. Follow the protons. NH3 before, after NH4 plus. What happened? Well, gee, I had 3 H's. Now I have 4 H's and a plus. NH3 accepted protons, right? Because before it looks like this, after it looks like this. So what do you call a substance that accepts protons? It's called a Bronsted-Lowry base. H2O before becomes OH minus after. What happened? Well, it was neutral and now it's negative. It had 2 H's, now it only has 1. This gave away an H plus. So we call that a Bronsted-Lowry acid. So in order to read this, you need to look at the left side and say, this is before, this is after, what happened? And we assign it to this side. Now let's read it in the reverse. Now this is before, this is after. So look, NH4 plus becomes NH3 neutral. So what happened? I had 4 H's, now I have 3. I had a plus charge, now I don't. So this is given away an H plus. So that is an acid. OH minus is now H2O, neutral charge. So it looks like I gained an H plus. That's called a base. And if you notice, the base on the one side and the acid on the other side look pretty similar. The only difference is one of them has more, one of them has more H's. And so that's something called conjugate acid-base pairs, which I have not seen on the Regents in a while. So regular college prep students, I wouldn't really focus on conjugate acid-base pairs. I think you should mostly focus on, in an alternate theory, an acid would, and you would say, oh, the alternate theory is Bronsted-Lowry, which means an acid would donate or give away protons, or H plus. Yeah. Let's take a quick trip. Oh, I had all this. Frustrating. Let's take a quick trip to table E, please. So it's on page 2. I'll wait while you get there. Table E, what is hydronium? It's the very first one on there. Hydronium is H3. Hold on a second. Sorry, I just had to take a sip of water. Now back to hydronium. Notice water is very similar to hydronium with one little change, an extra H plus. So hydronium is essentially a water molecule that has gained an H plus. And since all acids are aqueous, remember, dissolved in water, it's pretty much the same thing. So H3O plus, that is hydronium. It's pretty much equivalent to aqueous ions. Self-ionization means that water molecules in a container of water are constantly going to be breaking apart and then also getting extra things. So notice we've got 2 water molecules here. Some of them are going to gain protons and become hydronium. Some of them are going to lose protons and become hydroxide. And then also, while that kind of change is happening, there's going to be other times when hydronium ions are going to be losing protons and becoming water, and hydroxide ions are going to be gaining protons and becoming water. So in your glass of water, you got a whole bunch of changes going on. You've got water molecules grabbing protons, you got water molecules losing protons, you got hydroniums losing, you got hydroxides gaining, and it's all happening as it just sits there. Final thing, again, mostly for honors. Again, if you were in just a regular college prep, feel free to continue listening because it's interesting and you've already talked about Bronsted-Lowry anyway. So in Bronsted-Lowry theory, substances that differ by a proton are called conjugate pairs. So if you look here, HCl becomes Cl minus. HCl loses a proton to come to here, so we call it the acid. Don't go away. H2O becomes H3O plus. So what happened? It looks like it gains. That's why it's called the base. And in the reverse, H3O plus becomes H2O. We lost, so that's an acid. Cl minus becomes HCl, so it gains. It's a base. So you just pair them up. HCl and the Cl minus. Those are just about the same except for one proton. Pair these guys up. They're just about the same except for a proton. So we call those conjugate acid-base pairs. Let's just give those a try, and then we'll be done. NH3 plus H2O, double reaction, NH4 plus OH minus. Okay, let's start by reading it in the forward, which is this way. NH3 becomes NH4 plus. What did it do? Before, after. Looks like it gained a proton. So if you gain a proton, this is called a base. If you have H2O, then it becomes OH minus. That must be an acid. Now let's look in the reverse. If NH3 was a base here, that makes this the acid. Let's make sure that works. NH4 becomes NH3. Looks like I've lost a proton. That is the definition of acid. And if this is acid, this must be base. And yeah, that makes sense. So let's do the conjugate acid-base pairs here. So the base on this side and the acid on that side, that's what we call a conjugate acid-base pair. What's the only difference? A proton. Here's the other pair. And I forgot we were doing some of that too. All right, let's take a look here. Now, this is acetic acid. It's on table K. This whole thing is called acetate, and it's negative. This is H+. Okay, so let's take a look. We have H acetate becoming just acetate minus. So look, it obviously lost. So this whole thing is called an acid. This becomes this, so it's a base. Then you look and see who's similar. H2O, H3O plus, hey, that's pretty similar. That's got to be acid because the opposite here. Acid here, base here. And if you don't want to like kind of jump ahead, break it down. H3O plus becomes H2O. What happened? Oh, I lost a proton. One less H, now I'm neutral instead of positive. That makes me acid. So where are the conjugate acid-base pairs? Here and here. Okay, that's it for today. Thanks for watching.